everyone, today we are going to build the Deep Convolutional GAN or the DCGAN. So if you look back at our original Intro to GAN video, you'll remember that we generated very simple images, MNIST images, using linear layers. But of course, a linear layer is not all that helpful when it comes to image generation, right? We saw at the very beginning when we looked at our Intro to PyTorch, the Intro to Vision stuff. Linear layers are not all that good at processing images because it loses the spatial correlation aspect of an image. On the other hand, convolutions take advantage of that. And so, of course, we can assume that generating images using convolutions should be much more powerful to create much more high quality image representations than it would be with just standard linear layers, especially for more complicated images. So today we're going to be looking at the Celeb A Faces dataset. You can go ahead and just download it from Kaggle or wherever else. It's basically just a folder full of pictures of faces, nothing crazy. So we'll take a look at that in a bit. Just a couple details. The DCGAN implementation, about 90% of the code will be basically identical to what we had done earlier. The main novelty is the model is going to look different, but the training and stuff will look about the same. But there's a couple of small details that we want to talk about. So first of all, we start with, again, just like before, and again, we start with some random noise, and instead of using linear layers, we're going to use convolution layers to kind of upsample it up to the image space that we want, right? The image size that we want. And here you can see there's 64 by 64 image size, and then 3 channels because they're going to be RGB images. So that's our initial goal, right? That's what the model is going to look like. There's going to be a bunch of convolutions. In this case, they're going to be transposed convolutions because we're going to be upsampling the image, right? So they're going to be transposed convolutions. And so that's step one. We're of course going to have a discriminator as well. It's again going to be a convolution-based discriminator. We'll kind of see that in a bit. But there were a couple of implementation details that I want to mention that the paper found especially helpful in training. Number one, because of the unstable nature of GANs, they found that adding batch norm to every single layer except for the last layer of the generator and the first layer of the discriminator seemed to improve training effectiveness. So that's number one. Number two, they use the leaky ReLU activation rather than ReLU, and this allows for some of that negative information to flow, because if you do ReLU, remember anything less than 0 becomes 0. So that information is completely lost, which means when you do gradients, that negative information gradient also disappears. So this will kind of preserve a little bit of that. In the generator, they found that ReLU seemed to work best. So we're going to be having leaky ReLU in the discriminator, but ReLU in the generator. There's no more fully connected layers, of course, that's going to be going away. And they also found that it's best to initialize all the convolutions and batch norms and stuff from a Gaussian normal distribution, right? So we're going to go ahead and initialize that as well. So imports are same as always, right? Nothing crazy here. Let's just go ahead and start building the model. And I think that will be enough for you to understand exactly what's going on. So let's start with the generator, the most interesting part. So class generator nn.module def init self, and what we need to provide is a couple pieces of information. Out channels, right? So we know these are going to be 3 channel images, RGB images. So it's going to be 3. And then in channels latent dim is 100, right? So basically, again, if you remember from our again, we need to create some noise with some latent dimension, right? So whatever we wanted. So we picked 100 there, we're picking 100 here, but it's going to be a little bit different because we're doing convolutions rather than linear layers, and we'll talk about that in just a second. So first of all, let's do self dot, let's just store some of this information. Out channels is out channels, self dot, latent dim, let's just do latent dim, keep it short. Latent dim is going to be in channels latent dim, and let's go ahead and define our generator, self.generator, and nn.sequential. So I'm already assuming you know what a transpose convolution is, so let's just kind of take a quick look at how we're going to use it. I'm just going to define one of these transpose convolutions, and then we'll stack the rest on in just a bit. So the first one's going to be a nn.con transpose 2D, and the input is going to be the latent dimension. So what did we pick for the latent dimension? It's going to be self.latent dim, right? That's where we're going to start. And we're going to follow the paper implementation. So they go from latent dim to 1024, right? So we're going to go straight to 1024. Then we're going to go from 1024, 512, 512, 256. We're just going to follow the pattern, right? So let's just go to 1024 first, and then we'll come back to it. And what we want to do is notice the resolution here. We go to a 4x4 image space. Okay, so how do we get that? We can use a kernel size of 4, right? So we're going to do a kernel size of 4. A stride of 1, we're going to move 1 at a time, and we're going to set bias to false right now because we're about to add in a batch normalization, so the bias doesn't really matter anymore. So that's our generator. We're going to write more, but let's just try to get some examples, see how this exactly works. We're going to do forward self x, and what we're going to do is just do return self.generator x. And so let's create some data. So rand is torch.randn. And if you remember, when we generated random noise for our linear layers, right? Linear layers expect some batch size, let's say 4, by our latent dimension, which I've selected as 100. But convolutions want batch size by channels, by height, by width. So what is the height and width in this case? Well, let's just start from a 1x1 tensor. So it's just a dummy dimension, right? So it's just basically we're saying we have 4 images. Each image is 100 channels, and each channel is of size 1 height by 1 width. And what we're going to do is take this 1x1 and upsample it by a factor of 4. So you have a 1x1 here, and you upsample it to a factor of 4x4. And that's what our transpose convolution is going to do. So let's go ahead and apply it and see what happens. So we're going to call this gen. This is our generator. There we go. And I also forgot the super dot init. There we go. So that's our generator. And into our generator, we're going to pass in the random. And then we're going to take the shape. And you can see we went from 4x100 by 1x1 to 4x1024 because I specified 1024 output channels. And our 1x1 image resolution is basically just 1 pixel by 1 pixel, so it's just a single pixel, was upsampled to 4x4 pixels, which follows exactly what we have up here, right? 4x4. So we're good to go. So that's an upsample factor by 4. Once we do the convolution, let's go ahead and do the rest. So after convolution, we're going to do a batch norm. So nn.batch norm 2D. And this should be a comma. Batch norm 2D. And this is going to take 1024 because this has 1024. So we're good to go there. And then we'll do a ReLU because like they mentioned, they found that ReLU seemed to work well in the generator, but we'll be doing leaky ReLU in a bit for the discriminator. So we're good to go. So that's step number 1. That's our first set of convolutions. Now let's just go ahead and rinse and repeat, right? We're going to stack a couple of these on top of each other. Let's see, 1, 2, 3, 4, 5. All right. And let's kind of make the necessary changes. So like we saw in the figure, they went from 1024 to 512, then 512 to 256, 128. They sort of kind of follow exactly that same pattern. So now that we're at 1024, this is going to be 1024, and we're going to go to 512. Right, and again, we're going to do a kernel size of 4, but let's actually comment all of this out for now so we don't have to see it. And let's just leave everything else the same right now and see what happens when we run it. Now you can see we went up to a 7x7. Now, is that what we want? Let's double check. We want it to go to a 8x8. So it looks like we're a little off, and this is a standard, like, you're off by 1 problem in your transpose convolution. There's a bunch of ways we can deal with this. One way we can do it is we can say output padding equals 1. Actually, no. That won't work here. That's my bad. Let's do a stride of 2 and a padding of 1, like that. Now you can see we're up to an 8x8, right? So basically we're going to take twice as many steps. So we're going to do same kernel size. And this will essentially go double it up because we're moving 2 at a time, but we're adding an extra padding around the side just so we can skip over to the edges, right? So we can kind of go over. There's actually a bunch of ways we could get to the 8x8 if we wanted to, but with a kernel size of 4, this is the way to do it. We could also use a kernel size of 3, but then you'd have to mess with the stride and the padding and stuff like that. So for now, I'm not going to mess with it all that much. We're going to stick as close as we can to the implementation. So this line now gets us to our 512 by 8x8. Which is exactly what we wanted, right? We have 512 by 8x8 for this first set. And then again, we want to do 256, 16 by 16, and then 128, 32 by 32, so on and so forth. So now we can go ahead and uncomment all of you. This is going to be 512. That means this is going to be 512, and this is going to be 256 as indicated in the paper, which means this is going to be 256. Then this is going to be 256, and we're going to go down to 128, and then this will again be 128. And then this last one's going to be 128, and we will have out channels here, right? So however many output channels we have. So self.out channels is what will go right here. And let's go ahead and update the rest of this. So we want a stride of 2 and padding of 1 for each of these, because we want to upsample by 2 every single time. So we're going to do stride of 2, padding of 1. So stride of 2, padding 1, stride of 2, padding 1. And so we're good to go everywhere here. This should be 128. That's everything we need. And now 1, we'll also have that here. So stride of 2, padding 1. Now, remember here, if we take a look back at some of our implementation details, we have our, they found that in the, let's see here. Which line was it? All right, so having batch norm in every layer except the last layer of the generator and the first layer of the discriminator. So we're gonna kind of remove this batch norm from here, right? So no batch norm. And now that we've removed the batch norm from here, that means this bias doesn't need to be false, right? Because the batch norm essentially negates the bias. So if we don't have a batch norm, we should keep the bias in there. So we're good to go. That gives us everything we need. And also ReLU is not the correct activation function. Our images, this depends on how you do it, but I'm going to scale the images between -1 and 1, right? So all of our images will be -1 and 1, which means our generator should generate pixel values between -1 and 1. So to do that, we can do nn.10h. And 10 hyperbolic will generate between -1 and 1. And now you can see we take a batch size of 4, 100 channels by 1 pixels, height width, and it outputs a 4 by 3 by 64 by 64, which means we're generating a 3-channel image, each channel being 64 by 64. So that's the pixel resolution. And that's basically it, right? That's our entire generator, and we're good to go there. We'll come back and write the initialization, the kind of custom weight initialization, in just a second. Let's go ahead and do the discriminator now. So we're going to do class discriminator and then .module def init. This is going to take self and just how many in channels. Self in channels is 3. And super.init, just like that. And so now what does our discriminator look like? So the discriminator is basically just a classifier, right? The purpose of a discriminator is to take in our generated images and our real images, of course, which will be in this shape, right? So our data will be in this shape, and the discriminator's job is to take this data and then classify, is it real or is it fake? Okay, that's no problem. All we need to do is just do a bunch of convolutions, like a regular convolutional neural network for classification, and just build that. And so you can obviously make this look however you want it to. We're just gonna follow the paper implementation as close as possible. So they recommend we will first do discriminator is nn.sequential. Good. And the first one's going to be a nn.conv2d, right? nn.conv2d, and it's going to be in channels. And so in channels is going to be, remember, it's going to be getting, let's actually go ahead and generate some random data. We know our data is going to look like 3 by 64 by 64, right? That's what our images are going to look like. So let's do our discriminator. Disc is our discriminator, which means this is our discriminator. We're going to pass our random data in. Let's throw a forward function in there. Def forward self x and return self.discriminator x. Looks like, yep, we need to add the rest of this in. So the input is going to be 3 channels, or whatever the input channels is. So we're going to do 3. We're going to do 64. We'll do a kernel size equals 4, stride equals 2, padding equals 1, and bias equals false, because we're going to follow this up with a batch norm in just a second. Or we won't actually, because they, again, recommended that except the last layer is generator or the first layer of the discriminator, right? So we're not going to have a batch norm in the first one, so we can actually leave bias off here. There we go. So that is our first convolution, and you can see it downsamples by a factor of 2. So there we go. We're now down to 32 by 32 with 64 channels. And so now we can do a nn.leaky ReLU, right? So leaky ReLU 0.2. So Leaky ReLU, again, as recommended, and the weights typically used, so the slope for the leaky ReLU. If you don't know what leaky ReLU looks like, I can pull that up real quick. So leaky ReLU looks kind of like this. Oh, let's pull it in. Here we go. Looks kind of like this, right? It's just, instead of ReLU where it zeroes everything out, you have a little bit of negative slope here. Or your negatives have some, gradient information that can flow in. It's not just zero. So there we go. That's our simple leaky ReLU. And so we have that right there. Let's throw a comma in there. Comma. All right, up next, nn.conv2d. If our previous channel outputted 64, this is going to take in 64. We're going to have 128. Kernel size, again, 4. Stride equals 2. Padding equals 1. And now we're going to do bias equals false. And then we just follow it up with a batch norm and a leaky ReLU. So nn.batch norm2d, 128. And then nn.leaky ReLU 0.2, just like that. And we'll just repeat this a couple more times. So each of these are going to downsample by a factor of 2. So this is down to 32 by 32. This will be then down to 16, 8, 4, so on and so forth. So let's just update all these numbers here. So this is going to go from 128 to 256. So this will be 256. And then we're going to go from 256 channels to 512 channels. Again, this will be 512, leaky ReLU. And then, let's see what happens when we apply all this. We can see we're down to a 4 by 512 by 4 by 4. So we're pretty close. Let's do one more, right? One more convolution, nn.conv2d. It's going to take in 512 channels, and it's just going to output one channel. Again, kernel size equals 4, stride equals 2, padding equals 1. Actually, this time it's thinking padding equals 0. Yeah, padding equals 0. And we can see we're now down to a 1 by 1 by 1, which is really just 1, right? So if we take a look at this, we've produced a single number for each one of these things. Because remember, we're going to be passing this to the binary cross-entropy loss. So BC loss expects a single number per sample. And then when you apply sigmoid to this thing, it'll either be greater than 0.5 or less than 0.5, indicating is it real or is it fake? So nothing has really changed. The only thing that's now really different is that in our standard GAN setup, right, when we had done it earlier, we just had a 4 by 1, and that was it. But now we just have these 2 extra dummy dimensions here that just come from the fact that we're using a convolution. We could squeeze them out now. We wouldn't need them. We could do a dot reshape -1, 1. And this would also be just as valid, right? Because once we kind of have this output, we don't really care about those extra 1 dimensions. They're just dummy dimensions that exist there. So we can leave it like that, right? Reshape -1, 1, and we get our 4, 1. So for every sample we predicted, is it real or fake based on this one number, right? The logit, the raw logit of that number. And so now we're good to go here. Let's go ahead and add that custom weight initialization in. So as it was recommended, def init weights, and we're going to do module. And we're going to do if is instance. So if we're looking at if the module is a nn.conv2d, so if it's a convolution, or a nn.conv transpose 2d, so if it's a transpose convolution, or if it's an nn.batch norm 2d, if it's any one of these things, then we're going to go ahead and do nn.init.normal. We're going to normally initialize, right, in place. We're going to normally initialize the module.weight with a standard normal. So we're going to, or not standard normal, with a Gaussian distribution with mean 0.0 and standard deviation 0.02, right? So that's our, that's how you can initialize weight. So we're basically saying we want to initialize module.weight with a normal distribution with mean 0 and standard deviation 0.02. And then similarly, we're going to do if module.bias is not none, because not every single convolution or transpose convolution will have a bias because of those batch norm. It's a sanity check. If it's not none, if we do have a bias, then what we're going to do is nn.init.constant, and we're going to initialize the module.bias with just a bunch of zeros, right? This is, again, the recommended initialization. So how do we actually apply this? All you need to do is in your initialization of the model, like in the generator, we can just do self.apply init weights. You basically call the function init weights inside self.apply a method already built into all PyTorch modules, and you're good to go. This will recursively go through all of the layers and basically reinitialize the weights as you want, rather than the default initialization strategy that all of these layers already have. So self.apply init weights, and similarly self.apply init weights. And we are now good to go. So that's basically it. That's the novelty of our model. We have a generator, discriminator. The only difference is we just don't have any convolutions anymore, right? It's all being done with linear layers. Nice. All right, so now to wrap it up, we're going to just talk about a couple of details, and then the training will be basically the same as before. So I'm not going to spend as much time on the training loop. You can take a look at that in previous videos. I'm going to go ahead and just copy some of this stuff in because no one wants to see it. It's just me just defining, device, image size, all the standard stuff that we want to use to train our model, just to define everything. And so we're good to go. So let's go ahead and define our data set, data loader real quick. So if you again remember, we're going to be doing the celeb A, the faces data set. And the faces data set basically is a folder full of just images. So if you do os.lister and I do, here, let's see. I think I have it in this path. So here we go. And then inside here, we have this image align celeb A. And then we will have this folder right here. You can see it's basically a huge folder full of JPEGs, each of these JPEGs being a image, right? A picture of some face. So what we're going to do is just do image folder on this path right here. So we're going to do dataset is equal to image folder, which we imported earlier. And it's going to be to this path right there. Right? And then we can do for sample in dataset, print sample. Let's throw a break in there so it doesn't print all of them out. And there's one of our images. We can take a look at them. Let's look at one, display. We can do sample 0. And you can see it's a picture of a face, right? Exciting stuff. So now that we have that, let's go ahead and do the rest. So these are pill images. We need to actually convert them to tensors. So let's do that. Transforms is going to be transforms.compose. And we're going to first do, right, standard transformations, transforms.resize. And we're going to resize it to our image size by image size, which we know is 64 by 64, right? That's what we're working with. So we're going to be doing image size by image size, just like that. After that, we need to convert it to a tensor. So we can do transforms.toTensor, right? Convert it to a tensor. But remember, these tensors are going to be between 0 and 1. But we want them to be between -1 and 1. That's how we scaled it. And that's why we did 10h right here. If we kept it between 0 and 1, then we could use sigmoid here instead, right? So sigmoid would have done it between 0 and 1. We want it between -1 and 1. Well, how do we convert 0 and 1 to -1 to 1? So I think we've done this before, but just as a reminder, if we do 0 to 1, if we divide, or if we first subtract 0.5, then that will give us -0.5 to 0.5. And then if we divide by 0.5, right, that will give us -1 to 1, right? That's how we're going to get to -1 to 1. So we can say that we want to normalize these images with a mean of 0.5 and a standard deviation of 0.5, because that's how we standardize data, right? You take data, subtract the mean, divide by the standard deviation. So we can just provide it exactly that. So we can do transforms.normalize, and we're just going to use 0.5, 0.5, 0.5. So for each channel, RGB, we're going to have a mean of 0.5, and then we're going to have a standard deviation of also 0.5, 0.5, 0.5. And this just ensures that our pixel values are scaled between -1 and 1. So we're good to go there. We actually need to apply this transform. So this is going to go here, transform equals transforms. And now we can do our for sample in dataset, print sample. Let's just look at the image because we don't really care about the label. Compose has no attribute compose. What am I missing here? Oh, I made a small mistake. I overwrote this transforms variable. Let's fix that. This is not going to be transforms. Let's call it image transforms, right? We can do that. And we can name that here. And now we're good to go. So here's all of our numbers. See, we have negative values and positive values. So everything's scaled between -1 and 1. Nice. Data loader is pretty simple. Data loader is going to be our data loader on our data set. Batch size is going to be the batch size that we indicated. Shuffle is of course true because we're training stuff. So there we go. Num workers equals num workers, and we can do pin memory equals true. So we are now good to go. Let's go ahead and define our models now. So we're going to do our generator. It's going to be the generator that we spent all that time writing. Out channels is equal to our image channels, right? So it's 3 in our case. And then our in channels is just going to be the latent dimension, right, that we picked. And it wasn't in channels, it was in channels latent dim, right? So that is our generator. If we take a look, generator, it is a model that starts with 100 channels because that's the latent dim we picked, and then just follows the pattern that we already selected. So we are good to go. Similarly, the discriminator is going to be the discriminator. It'll be in channels equals image channels, right? So how many channels are we doing? And we want to make sure both of these are on the GPU, so we can do .to device, .to device. Simple as that. Now, here's one really key idea, a small detail we didn't really talk about last time, but is important for us to discuss a little bit. And this is the Atom optimizer, and just a little bit about how it works. So first of all, we'll have a gen optimizer just like we did before. And before, all we did was optim.atom, and we'll do generator.parameters, right? There you go, there's our model. And then we'll have some learning rate is our learning rate. And that was it. And similarly, we did our disk optimizer is equal to optim.atom. This will be the discriminator.parameters. And again, our learning rate is equal to the learning rate, right? Whatever we set. We could also have different learning rates for the generator and discriminator, but that's fine. For now, this is fine. But the Atom optimizer actually has another really important parameter that we haven't looked at. So if I look at Atom, PyTorch, just pull this up real quick. It has something known as the beta 1 and beta 2 parameters. That's here, betas. So the first one is beta 1 and the second one is beta 2. And these are the defaults. 0.9 and 0.999, sorry, 3 nines, is the default that this model uses. And what you can see, let's try and kind of look at here. So coefficients used for computing running averages of gradients, and it's square. Okay, what does that exactly mean? I might, if y'all are interested, I can do a whole video on Atom one day, but for now it's fine. But you can see that our beta 1 and beta 2 is a weighting term. We can see that for our gradient, or basically the weight that we want for a gradient at mt, so at time t, or basically iteration t, we're going to take beta 1 times mt minus 1. What was the gradient at the previous step? Plus 1 minus beta 1 gt. So mt minus 1 is kind of our history of gradients, right? How much of the previous gradient information are we storing? Or basically, you know, the moving average up to that point, plus 1 minus beta 1 of the current gradient. And similarly, we do the exact same thing, but v is on the square of the gradients. And so what these are is basically your first moment and second moment estimates of the gradient is the best way to think about it. Now, in all practical terms, the way to think about this is beta 1 and beta 2 are just weighting factors. And what this means is a larger value for beta, like the 0.9 that it's initially set to, means there's less decay. You're putting more emphasis on the historical information that you stored, mt minus 1. And similarly, a large beta 2 means you're putting more information on the historical information of the square gradient right here. So that's kind of the key idea. The larger the beta, the more emphasis you're putting on the historical accumulated gradient information. And it's kind of an exponential decay. So as you would imagine, the smaller beta becomes, the less emphasis you put on your historical data and more on the current gradient, because gt and gt squared, right, the square of gt, is your current gradient information, as you can see here, right? That's your current gradients. And so this is the key idea of the beta parameters, because if you pick a large value, you're putting more emphasis on historical gradient values, whereas reducing it will put less emphasis. And so for the GAN specifically, typically for all the other models we've been looking at, this is actually pretty good. It allows you to smooth out big spikes in gradients and things like that, so it's okay. But in the GAN, this 0.9 actually leads to a problem. And the problem is that your generator and discriminator are fighting against each other. And if your generator and discriminator are looking to the past too much, putting too much emphasis on the history of gradients that it's been, accumulating as it's been training, then your model is able to less quickly respond to sudden changes in the gradient. You want your generator to quickly respond to the discriminator, and you want the discriminator to quickly respond to the generator. But you're hampering it by essentially saying, I want you to update with the history of yourself. And that's probably not a good way to train a GAN model, because the GAN needs to quickly update. You need to quickly have the generator say, oh wow, the discriminator is picking up on these features, and I need to make sure that these don't exist and better match the data distribution. And similarly, the discriminator needs to see, oh wow, the generator is getting really good at this. I need to find a different set of features or get better at being able to identify between these things. And so this is exactly kind of a problem that we have. And so similarly for beta 2, right? Beta 2 set to 0.999, it's the estimate of the history of square gradients, right? And it gives a good information actually about the variance of the gradients and how large they have been. For the beta 2, we just leave it alone. We're not going to really mess with that. And because beta 2 is actually really good for smoothing our gradients to sudden changes. If beta 2 isn't high enough, then we might have a problem with unstable training in general. Right, so the typical strategy used is we're going to set beta 1 to 0.5. So we're going to be putting more emphasis on or basically half and half, right? 0.5 is essentially saying we want to put just as much emphasis on the history as we do on our current gradient. But for beta 2, we're going to leave it as 0.999 because that helps with general training stability, right? So these are just small details that are important in GANs, but we're going to go ahead and apply it right here. So that means we're going to set our betas equals, and this is why you'll often see 0.5, 0.999. It's to help with training, essentially. By setting this to 0.5, we're ensuring that our models, both the generator and discriminator, can quickly adapt to each other, right? Extracting the features they need or generating the features they need to be able to create good images or to be able to discriminate between real and fake images. But this 0.999, we keep it there just to make sure that our model training still stays stable, right? Helps with more stable training. And so we're good to go here. Now our loss function, just like before, right? It's just going to be nn.bce with logits loss. It's with logits because we never applied sigmoid to our discriminator. It's just raw logit output. So there we go. That's our output. And now for training this, we don't really, honestly, the 90% of this code is identical to what we had done before. So I'm going to go ahead and just copy some of the initial stuff, right? So I'm going to get rid of this just to make it as simple as possible. So there we go. This is the kind of what we had before for our GAN model. So for the unconditional GAN, one of the first ones we did, that's our starting point. And so what we're going to do is our gen losses and our disk losses, right? We have our two loss functions. We're going to go ahead and, we're going to have our two losses for generators and discriminators. We're going to go ahead and store them right there. And now that we have that, let's just go ahead and do what we always do. For epoch in TQDM, range epoch, so however many epochs we want to train for, we're going to do our generator epoch losses is an empty list. Our discriminator epoch losses is an empty list. And now we're going to loop through our data loader. We're going to do for images, and then it's going to return a class label, but we don't really care about them or really have any in this faces data, so we just ignore it. In data loader. So let's just go ahead and do batch size is equal to our images.shape0. And if we have, let's say, 64 samples in our batch, then we're going to first do, first we're going to make sure images is on the GPU, images.to CUDA, so device. And now we need to do our discriminator step, right? Discriminator step. And then we're going to do our generator step, right? Just like we did before. Much of the code will stay exactly the same. So first of all, we need to do our generator noise vector. So our noise, before our noise was torch.randn, and it's going to be batch size, randn, because we want Gaussian noise. It's going to be some batch size by some latent, right? Latent dimension. But remember, we are passing this to a convolution, which means we need to add the 1 by 1 as well, just like we did earlier, right? So nothing new. And then device equals device. After we generate our noise, everything else is going to kind of go the same way. So first of all, we need some labels for the discriminator and the generator. So generated labels is torch.zeros, right? So we're going to say the generated samples is of label 0. We're going to do batch size by 1, and it's going to be device equals device, just like that. All right, and then we will have our true labels, right? The true images is going to be labels is going to be torch.ones. Again, batch size by 1. There's a comma there. Device equals device. There we go. So that's our labels that we're going to use as our targets for the discriminator. Now that we have all that, let's go ahead and generate some images. So generated images is just going to be our generator. We're going to pass that noise in, so just like we did before. And we're going to go ahead and detach it, right? Because when we pass generated images to our discriminator, we don't need the gradient information of our discriminator step to update the generator. So we're just going to go ahead and detach it so that information, that backpropagation, never flows to the generator. Again, if you want more details for this stuff, just look at my Intro to GAN video where we talk a lot about this, kind of how gradients flow through this model. Good. So let's go ahead and just do exactly what we've done before. Real disc pred, right? So it's going to be our discriminator images. We're going to take our real images, give it to the discriminator, and then we're going to do our gen disc pred. This is going to be discriminator, and now we're going to pass in our fake images, right? Generated images. There you go. And now we need to compute our loss. So real loss is going to be the loss function between the real disc pred. And so our generator should predict that real images are real, so they get the true labels. And then our fake loss should be the loss function between the gen disc pred, and our generator should predict, our discriminator should predict that the generated images, right, generated images here are fake, so generated labels. Good. And so now that we have all of that, let's go ahead and compute our disc loss. It's just going to be our real loss plus fake loss divided by 2, just take the average. And lastly, all we need to do is just go ahead and store this. So we can do discriminator, let's see, epoch losses, so we're going to do that, dot append disc loss dot item. So there we go. All right, so that's all of our loss. And now before we actually update our discriminator, let's go ahead and zero out the gradient. So discriminator optimizer.zeroGrad, and go ahead and zero out those gradients. And now we're going to compute fresh gradients from this new step. And so it's going to be disc loss dot backward, right? Compute those gradients, and then discriminator optimizer dot step. And that's going to go ahead and update our discriminator. And that's basically it. Again, this code is all identical to what we had done earlier. So there's really nothing new here. The only new thing was this. Our noise vector, instead of just generating a single batch by latent, we now have these extra dummy dimensions in here because we're using a convolution, right, to do our generation. So there we go. Similarly, for our generator, this is going to be our noise is going to be torch.randan batch size, latent dimension, again, 1, 1. We're going to generate some new images here. So again, device equals device. And to our generator, we're going to first generate some images. Generated images is going to be our generator on the noise. We're going to go ahead and just generate some brand new images. And now we're going to pass our generated images to the discriminator. So gen discriminator pred is equal to, and actually let's just keep it short, gen disc pred is going to be discriminator generated images. And so again, the key idea here is to update the generator, we create some noise, we generate some images, and we pass our generated images to the discriminator. And now the most important part for the entire GAN loss setup, how we train a GAN, is our generator loss is going to be the loss function between the gen disc pred, right? Our loss function is gen disc pred, but we want our generator to be updated such that the discriminator thinks the generated images are actually real, right? So it goes backwards. So again, remember, when we computed our fake loss here, we wanted our discriminator to think that the generated diskpred are generated images, because they are generated images. But when we update our generator, we want to make sure that our generator is updated in the direction such that the discriminator thinks the generated images are actually true. And so we're going to be using the true labels here. And that's basically the big novelty of the GAN setup, right? So there we go. And now we can do generator epoch losses.append gen loss.item. There we go. And now, just like before, I'm gonna zero out the gradients of the generator. Generator optimizer.zero grad. Go ahead and zero those gradients out. Compute some losses. Compute your gradients. So gen loss.backward, and then generator optimizer.step. And we are good to go. And now the rest of this, I'm just gonna copy paste because it's just visualization code. Oh, did I miss it? Let's copy you. There we go. So again, this is all the same code from last time. Go ahead and average up your generator and discriminator, nothing crazy. For that epoch, just average up the losses, print it out so we can see what's going on. Go ahead and store them. And then after that, just go ahead and generate some pictures, which is pretty simple. What I'm doing here is set the generator to evaluation mode. And then with torch.nograd, because we don't need to compute gradients, generate a noise sample. I'm just going to generate 5 pictures. So there you go, 5 by latent dim by 1 by 1. Same setup. Pass our noise to the generator. Move it to the CPU after we generate it, and then just loop through the images one at a time and go ahead and plot them. And we just have to rescale the images. Remember, our images are between -1 and 1 right now, because that's what the tanh of the generator will create. So if we have -1 to 1, that means if we add 1 to it, that means it's 0 to 2. And if we divide by 2, then it's 0 to 1. So this will make sure our image is between 0 and 1. And if it's between 0 and 1, then we can easily go ahead and just use plt.imshow, right, to go ahead and visualize it. And so that is our generator and discriminator, everything set up. And we can now go ahead and train our model. Again, we don't need the label smoothing. And let's go ahead and debug some stuff. So we have invalid float tensor CUDA. Oh, okay, so it's something is not being created on the GPU. We have images here on line 32, generator noise, detach. I believe I moved it, but maybe I misspelled it. Oh, images, plural. All right, loss func is not defined. I believe I did. Oh, did I do loss fn everywhere, or did I do loss func? Loss func. I did loss func everywhere, so it should be func. And we should be, let's see. Okay, looks like it didn't break, but it's also not updating the progress bar. Oh, because the progress bar is on the epoch, yeah, so it's going to be 1 epoch at a time. All right. So this will take some time to train. We don't really need to watch this train. That's no fun to anyone. So what I did is I went ahead and plotted, and actually let's go ahead and see if we can do plot generation frequency. Let's do it every one. So every epoch, let's go ahead and plot it. And let's also do what batch size did we actually use? We used a batch size of 64, which is fine. It would probably be a little bit more helpful to get an idea of the timing if we actually had a TQDM here. And we can do leave equals false, so it disappears every time. There we go. So yeah, we can see it training. Again, watching a training loop is probably of no interest to y'all, so we can just look at the results here. And you can see initially the faces don't look all that good, but as you keep going, they get better and better. But yeah, that's basically the novelty. We didn't really change anything. Nothing fancy or new happened. All we did is just generated our images using a convolution, right? So we used a convolution to transpose convolutions to upsample and actually to generate our images. And then we had our discriminator, whose goal was to take those images, and it's basically just a classifier, a simple classification model that classifies, is it real or fake? And that's it. right? That's our DCGAN model, and it kind of sets us up for some more fun implementations in the future, like CycleGAN and stuff like that. Let's see if it actually plots. There we go. So we can see this is already starting to look like faces, so not bad. But of course, it will take more iterations to create some reasonable generations. I'm going to call it here. I will see y'all in the next one.